So I have the problem integral of x cube minus 2x plus 3 by x squared plus x minus 2 dx. So let's see how we can use partial fractions in order to integrate this using the partial fraction method. So as we see that the degree of the numerator is greater than the degree of the denominator, we can divide the two polynomials, polynomial in the numerator and polynomial in the denominator. And therefore, if I have this divided by this, let's see what is the division process going to yield through division algorithm. So x gives me, multiplied with x square, x cube plus x times of x square minus 2x. So this gives me minus x square, and plus 2x and minus 2x get cancelled and I get plus 3. But again, this can be reduced with minus 1, which gives me x square times minus 1 minus x square minus 2 minus 1, which is plus 2 minus x plus minus plus, is how we get 1 plus x. And let's see how this reduces to. Therefore, I can reduce x cube minus 2x plus 3 divided by x squared plus x minus 2 as so this is how we can just reduce this using this, and this. The quotient, the remainder, the quotient, the remainder, and the denominator. So once I obtain this, now integration of this is nothing but integration of the right hand side. And this is going to be integrated using some standard formulae and of course partial fractions. So let's see how we can integrate this, which is indirectly equal to this. Therefore, integrating on both sides, I get this to be x cubed minus 2x plus 3 by x squared plus x minus 2 of dx, which is integral of x minus 1 plus integral of this dx. Now let's split the integral using the expansion through brackets. That is, this step is followed with integral x dx minus integral dx, because this can be split as x dx minus dx under integral. Dx, and this is nothing but x square by 2 minus dx, because integral x dx using the formula x power n plus 1 by n plus 1 6, and we know that integral dx is x plus integral of this. Now how do we evaluate integral of this is the biggest question out here, which is connected with the topic itself, which is partial fraction method. Now it is very essential that I split this using the partial fractions. So let's see how I can split this term 1 plus x by x squared plus x minus 2 using the partial fractions. We know that this can be split as 1 plus x, and then I can find the factors of this as x minus 1 into x plus 2, because x plus 1 into x plus 2 are the factors for x squared plus x minus 2. Now this can be split as a by x minus 1 plus b by x plus 2 using the partial fractions. That implies a times of x plus 2 plus b times of x minus 1 is what I get with the denominator getting cancelled, is how we do in the partial fraction method. Now taking common, this is 2a minus b plus a plus b x, which is this. Now comparing the like coefficients, 2a minus b is 1 and a plus b is also 1, equating the like coefficients, and then using the elimination method we get this to be 3a equals 2. That implies a is 2/3 and b will be 1 minus 2/3, which is 1/3 when I substitute a in one of the equation. So therefore I got a is this and b is this, and hence my partial fraction. Therefore substituting the values of a, which is 2 by 3, and b, which is 1 by 3 in the partial fraction, I get this to be 1 plus x by x squared plus x minus 2 is a times of x minus 1 plus b times of x plus 2 is what we get this for this. And substituting this in the integral, I get this to be x squared by 2 minus x plus integral of this being substituted with 2 by 3 of x minus 1 of dx. Now when I split this brackets, expanding the brackets and using the integral separately, I get this to be 2 by 3 integral of 1 by x minus 1 dx, and this will be 1/3 of integral 1 by x plus 2 dx, which is simplified using x squared by 2 minus x plus 2/3 of, we know that integral of 1 by x minus a is log mod x minus a, and of course plus c. So integral 1 by x minus 1 is log mod x minus 1, and this is 1/3 log mod x plus 2 plus c, is how we obtain the integral. Therefore the overall integral of x cubed minus 2x plus 3 by x squared plus x minus 2 dx is x squared by 2 minus x plus 2 by 3 log mod x minus 1 plus 1/3 log mod x plus 2 plus c, and this integral is obtained strictly by using the partial fraction, this split into two partial fractions. So partial fraction helps in integration of few of the functions. Now let's see the reduction formulae in the topic of integration. So what is a reduction formulae? As we see, the word reduction is about reducing continuously, or reducing is the concept which we use in reduction formulae. So to go with the heading reduction formulae. So for example, I wanted to evaluate integral of x power n e power x ax dx. Let's see how we can evaluate this. As we clearly see that there are two functions, one is algebraic and the other is exponential, then clearly by using the IIB process, this comes first and this comes second. So taking this as the first function, and this as the second function, integration by parts uses the formula integral of first and second is first integral of second minus integral derivative of first into integral of second whole of dx is how we obtain. So using integration by parts, over here I have the first function which is x power n and my second function which is e power ax, and hence the formula reduces to first function integral of second minus integral derivative of first into integral of second whole of dx. Now this, on further simplification, gives x power n integral of e power ax is e power ax by coefficient of x, which is a, minus integral derivative of x power n is n times x power n minus 1, and this is e power ax by a dx, because integral e power ax is e power ax by a and derivative of x power n is n times x power n minus 1, using the standard formulae for derivatives and integrals respectively. And this, with n and a are constants, they come out and I get ax dx. Now let's see what happens if I reintegrate this, because this integration of x power n e power x dx is not completely simplified, but I got some reduction as x power n minus 1 e power x dx. Let's see what happens if I reintegrate this again by using integration by parts. Therefore, integral of x power n minus 1 e power ax dx, this being first function algebraic and this being second function, I have first into integral of second minus integral derivative of first into integral of second dx. This would be nothing but x power n minus 1 e power ax by a minus n into x power n minus 1 by a dx. So here again we see that this is reduced to n minus 2, and here x power n is reduced to n minus 1 and n minus 1 is reduced to n minus 2. Therefore we get a reduction where n reduces to n minus 1, this reduces to n minus 2, and again I simplified this using by parts, this reduces to n minus 3 and so on. Therefore we get a continuous reduction from n to n minus 1, n minus 1 to n minus 2, n minus 2 to n minus 3, and so on and so forth. Therefore finally it has to reduce to 1. Therefore we take this reduction formula of x power n e power x dx as x power n e power ax by a minus n by a, and this is taken as in minus 1. If I take this as in equals this, is how we see the formula. The formula says that in is equals this, which is this of in minus 1, where in minus 1 is integral x power n minus 1 e power ax dx, is how we call this as reduction formula for integral x power n e power ax dx. Now what is the significance of reduction formula is the biggest question out here. Let's see what exactly is the use of reduction formulae in evaluating few of the integrals. Now let's see the significance of reduction formula which we have taken, that is integral x power n e power ax dx. The significance so generally reduction formula helps in evaluating few of the integrals. Say for example, I wanted to evaluate integral of x cube e power 5x dx, then clearly I see that this, when compared with x power n e power ax dx, my n is 3 and my a is 5, is how I get it. Now I have the reduction formula for x power n e power ax dx is x power n that is, this is in minus 1 is what we get. Therefore, using this reduction formula of integral x power n e power ax dx, which is equal to x power n e power ax by a minus n by a integral of this, which is in minus 1. Let's see how I can evaluate this using this reduction formula. So in order to evaluate integral of x cube e power 5x dx, I have my n which is equal to 3 and a which is equal to 5. So n is 3 and a is 5. N minus 1, which is I2. This is In, therefore my I3 is equal to this, because the formula of In with n equal to 3 implies I3 is this times x cubes e power 5x of I2. And suppose I would like to find n is equal to implies my I2 will be integral of x square e power 5x dx, which I am going to find using n equal to 2, and here of course a is equal to 5. So n equal to is I2 equals x square e power 5x by 5 minus 5 by 2 integral, or this is I of n minus 1. So continuously I get this to be I1, which I am going to find using n equal to 1. So n equal to 1 and a equal to 5 gives me I1. Implies I1 using reduction formula is x power 1 e power 5x by 5 minus 1 by 5 integral, or this is I naught, because n is 1, so I naught is what we get. Now I naught is nothing but integral of x power 0 e power 5x dx, which can be evaluated using x e power 5x by 5 minus 1 by 5 e power 5x by 5, because integral of e power 5x is e power 5x by 5. Is what we get in terms of each. Now it is our duty to substitute each of I1 in this and I2 and I3 so that I get the entire problem using I1, I2 and I3. So let's substitute and see how we get each of them respectively. Therefore, substituting each of I0, I1, I2 in I3, we get I3 equals integral of x cubed e power 5x dx, with each of substitution stepwise gives us the overall answer as x cubed e power 5x by 5 minus 3 by 5 square x square e power 5x plus 6 by 5 cube x e power 5x minus 6 by 5 power 4 of e power 5x plus c is how the reduction formula reduces using I0, I1 and I2. So the significance of reduction formula is that for larger n, integrations can be simplified by reducing the value of n and then finding. So reduction helps for larger values of n in integration of the functions. Integration of I3, which is x cubed e power 5x dx, is done with this. Now let's see the reduction formula for sine power nx. That is, if I take integral of sine power nx as in, then this reduces to some continuous reduction which can be helpful in finding integral of sine power nx for larger values of n. So integral of sine power nx dx is assumed as in, and then sine power nx, which can be written as into sine x using the laws of indices. A power m times a power n is a power m plus n, which reduces to n. Now this is assumed as the first function and this as the second function, and then integration by parts leads to first function into integral of second minus integral derivative of first into integral of second of this. Thus, on further simplification, reduces to sine power nx, and integral sine x we know by standard formula is minus cos x minus derivative of this, which is n into n minus 1, n into x power n minus 1 into derivative of sine x, which is cos x, using the chain rule, and then integral of sine x, which is minus cos x dx, is how this is further simplified, and then rearranging minus sine power n minus 1x cos x and minus into minus, which is plus n minus 1 integral dx is what we get when simplified. Now we know that sine square x plus cos square x is 1, and therefore cos square can be written as 1 minus sine square. So this is replaced with 1 minus sine square. So cos square replaced with 1 minus sine square, because sine square theta plus cos square theta is 1, and then expanding by brackets we get this to be minus sine power n minus 1x cos x dx plus n minus 1 integral of sine power n minus 2x dx, and then replacing this minus of n minus 1 psi power n minus 2x sine square x dx is what we get when this is expanded using the brackets. Now, as I see this, I get this to be n minus 1x cos x and this is n minus 1 times in is integral sine power nx dx. So integral of sine power n minus 2x dx will be in minus 2, and this would be n minus 1 times sine power n minus 2 into sine square is sine power n using the laws of indices. A power m times a power n is a power m plus n. So n plus 1 cancels 2 and n is remaining. So this reduces, therefore in equals integral sine power nx dx is given by the formula minus sine power n minus 1x cos x plus n minus 1 in minus 2 minus n minus 1 in is what we get when I substitute this with the value as we have. Now taking in to the left, we get the reduction formula for in, that is integral sine power nx dx. Let's see how we can do continued from the session. So continued from here, my in further reduces to in equals, and this in also brought to the left will reduce this to in plus n minus 1 times in, which comes to the left, and the right hand side is minus sine power n minus 1x cos x, and this is plus n minus 1 in minus 2. So this on simplification gives 1 plus n minus 1 of in when I take common, and this is equals minus sine cos x is what we get. This gets cancelled and I get n times in is this of cos x of this. Therefore in is minus sine power n minus 1x cos x by n is how the reduction formula is obtained for integral sine power nx dx is minus sine power n minus 1x cos x by n plus n minus 1 by n in minus 2. Now let's take the odd and even cases of the reduction formula for integral sine power nx dx. Now as we know that the reduction formula for in, that is integral sine power nx dx, is given by the formula minus sine power n minus 1x cos x by n plus n minus 1 by n of in minus 2, then the biggest question is what would be the last term until the reduction. So here come the two cases. One is when n is even and when is odd. So for this, if n is even and n is odd, then interestingly we see that if n is even, this reduces to I0. Implies the last reduction is I0. And if n is odd, then it reduces in the form 7, 5, 3, 1. So here the last reduction is I1. So here the last reduction is I0, and in this case of n odd, the last reduction is I1. Therefore, let's calculate I0 and I1 in this case. Now, In is integral sine power nx dx. I0 is when n is 0. Therefore, simply substitute n equal to 0 in this formula. And sine power 0 is 1. So, 1 dx is x. That implies I0 is x. When n is even, the last reduction I0 is substituted with x, and here my I1 is when n is 1, and therefore sine power 1x dx, which is minus cos x. Therefore I1 is minus cos x, which we're going to substitute in case of n being odd. Therefore, if the value of n is even, my last reduction I0 is x, and if n is odd, then my last reduction, which is I1, is minus cos x, as we substitute here. Now let's see the significance of reduction formula for this, and of course this helps in evaluating integrals of this types for considerably larger values of n, or for any value of n being an integer. Suppose I have a problem which says integrate sine power 4x dx, then clearly this is identified as I4 with n equals 4. Now, as we know that the value of In is given by minus sine power n minus 1x cos x by n plus n minus 1 by n of In minus 2 as the reduction formula for sine power nx, taking n equal to 4, I get my I4, which is reduced to minus sine power 4 minus 1x cos x by 4 plus 4 minus 1 by 4 of this, by substituting n equal to 4 in the reduction formula. Now this would be by 4 plus 3 by 4 of I2, which is nothing but of I2, where n is 2. So to find I2, this reduces to minus sine 2 minus 1x cos x by 2 plus 2 minus 1 by 2 of this, by substituting n equal to 2 in case of this being equal to this. Now this would be by 2 minus sine cube x cos x by 4 plus 3 by 4 of by 2 of I0 is what we get. Therefore, I4 of this will be minus by taking expansion of the brackets sin x cos x plus 3 by 8 of I0, which is x, because we have found that I0 is the last reduction if n is odd, and then I get I0 is x. When n is even, I get I0, which is x. Is how we simplify integral of sine power nx using the reduction formula In, and then the answer for integral sine power 4x is minus sine cube x cos x by 4 minus 3 by 8 sine x cos x plus 3x by 8 plus the constant of integration c. Reduction formulae connected with integration. Now let's see the reduction formula for integration of the type sine power mx cos power nx dx, where m belongs to z plus the positive integers and n belongs to z and n is always greater than or equal to 2. So are the conditions through which we are going to integrate sine power mx cos power nx dx. Generally, integral of sine power mx cos power nx is denoted by Imn. Now Imn is integral which on reduction through integration by parts leads to the answer as 1 by m plus n cos power n minus 1x sine power m plus 1x plus n minus 1 by m plus n Im n minus 2 is how we get the reduction formula for Imn integral sine power mx cos power nx dx as the formula 1 by m plus n cos power n minus 1x sine power m plus 1x plus n minus 1 by m plus n Im n minus 2 is how we get the reduction formula. Therefore, as if suppose I wanted to find the integral of I32, that is integral sine cube x cos square x dx, then I assume my m is 3 and my n is 2 and then use the reduction formula, which in the next stage reduces to I32 reduces to I30 where n is 0 and then finally the whole of reduces to Im, and then I can use this with connected with the previous session of Im, which is I30 is Im, that is I3, which is calculated using integral of sine cube x dx as done in the previous session. So In is calculated and then the whole answer is obtained for I32 in each of the case. So reduction of n is connected with m in the whole problem in this manner. Say for example, I take I32 connected with this. Now let's see the reduction formula for tan. So if I would like to evaluate integral of tan power nx dx, where n is an integer and n is greater than or equal to 2, then we use the similar reduction formula, assuming In equals integral tan power nx dx. This reduces to the form tan power n minus 1 by n minus 1 of this, where I have two cases for this, the odd and even case, n even and n odd. Then if n is even, my last reduction reduces to I naught because 6, 4, 2, 0, etc. And this will be integral of tan power 0x dx, which is x. I get I naught is this, and here the last reduction will be I1, which is integral tan x, which is log mod secant x plus c. So integral of tan x is log mod secant x, which is I1, and this is I naught. So if n is even, the last reduction is x, if n is odd, the last reduction is log mod secant x plus c, which we use accordingly with n. Now next is the reduction formula for integral secant power nx dx for n belonging to z and n greater than or equal to 2. So as in case of integral tan power x, similarly I take my integral secant power nx dx as in and then expand this using the reduction formula, and I get this to be 1 by n minus 1 secant n minus 1 n minus 2 tan x plus n minus 2 by n minus 1 of I is what we get in integrating this equal to this. So the reduction formula for secant power nx is this, which we get. Now let's see the last reduction for n even and n odd. Let me take two cases where n is even and n is odd. Clearly we know that if n is even, it reduces in the form 8, 6, 4, 2, 0. So my last reduction is I naught, which is nothing but secant power 0x dx, that is x, because this reduces to integral dx. And when n is odd, my last reduction is I1, which is secant power 1x dx, where integral secant x is log mod secant x plus tan x plus c. So for n even, the last reduction for integral secant power nx dx is x, and for n odd, my last reduction for this is log mod secant x plus tan x plus c. Is how we understand the last reductions with the two cases n even and n odd. If suppose I have integrals of the form integral e power x times f of x plus f dash x dx, then we have an exclusive formula for integrals of this type. So let's see the derived formula for integral e power x times f of x plus f dash x dx. So integral of e power x times f of x plus f dash x dx is directly given to be e power x f of x plus c. This will be directly multiplied with this, is what we get as the formula in case of this integral. So whenever we find an integral of the form e power x times f of x plus f dash x dx, if you can express these two terms inside the bracket as derivative of each other, then directly I can obtain the answer as e power x to that of the function, is what we get here. So let's see some example problems connected with this formula. So for example, I have to evaluate integral of e power x times x plus 2 by x plus 3 whole square dx. Now let's see if I can use this exclusive formula in integrating this when this is converted into the form f of x plus f dash x. So let's try to split the terms out here. Now as I see here, I can further modify this function by taking x plus 2 written as x plus 3 minus 1, because 2 is written as 3 minus 1. Now the idea behind writing 2 as 3 minus 1 is to make these two to be similar, so that I can split and I get the simplification done easier out here. So this can be split as x plus 3 by x plus 3 whole square minus 1 by x plus 3 whole square. So this is split as this by this minus 1 by this dx. So the function gets split into x plus 3 by x plus 3 whole square minus 1 by x plus 3 whole square. Now clearly I see that 1 of x plus 3 gets cancelled, and this reduces to the form integral e power x of 1 by x plus 3 minus 1 by x plus 3 whole square of dx. So this is the final representation where I get this. Say I take this as function f of x. Let's see if the other term gets to be f dash x. Now clearly I see that f of x equals 1 by x plus 3 implies f dash x is minus 1 by x plus 3 whole square, as using the derivative formula leads to this, which is nothing but this, as written as minus 1 by this. So if this is f of x, this is f dash x. Now clearly I observe that this is in the form of e power x times f of x plus f dash x, which is given by the formula e power x f of x plus c. Therefore, integration of e power x times x plus 2 by x plus 3 whole square dx, which is the given problem, is nothing but e power x by x plus 3 plus c. Integration of the form e power x f of x plus f dash x dx is used to integrate this to be equal to this.